All right, so now we're going to work on worksheet 5. This is the bottom half of the CVPM worksheet 4 and 5. So this worksheet here is kind of our transition into the next unit, which will be constant acceleration, which will make things more complicated, but we'll kind of see what we've learned so far, what it can actually be used for. And they give us 3 scenarios. So they give us 1, 2, and 3. The first one is this object, this Mack truck speeding up. The second one is the dune buggy traveling at constant speed. And the third one is a driver who brakes because they see a deer in the distance and they don't want to hit it. So which one can we use CVPM? And I'll let you guys think about it. You can pause the video. The answer is scenario 2. So everything we've done in this unit so far is basically something that is just moving at one speed. And if it changes speeds, it changes to a constant speed that whole time. It doesn't gradually change. The next unit will account for this gradual change. We'll have to use acceleration, essentially. I would explain it more, or like what I'll say here is this one is speeding up. This one's slowing down. So both of those are things we can't use for CVPM. All right, so the only one I can use is scenario 2, and I'm going to draw all the graphs I know I can use for it. That's a motion map, a position time graph, and a velocity time graph. So this object is traveling 20 seconds at a speed of 8.5 meters per second. You know what? I'm just going to call every dot 4 seconds. And what that will allow me to do is just represent this with 4 dots. I'm going to make my motion map. Overall, so I'm going to go 20 seconds at 8.5 meters per second. I'm going to take this time to explain what this whole unit was about. This seems like a good time as any. When I looked at a position time graph, I have this slope here. And this slope I can figure out is x over t, and that gave me the velocity of an object. So velocity was x over t. When I had a velocity time graph, the area underneath it, which I could solve by going v times t, was equal to my displacement. And so I have these two formulas here. I have v is equal to x over t, and I have x is equal to vt. And it turns out these are the same formulas. This one is just slope, and this one is just area, right? It's dependent on these graphs. So if I want to go from a position time graph to a velocity time graph, I take the slope. And if I want to go from a velocity time graph, I take the area. And with that knowledge, I'm going to make my motion map. Maybe I should actually go with my position time graph first. And I'll say, okay, we have this object. I'll assume it starts at 0 meters and we travel for 20 seconds. And I know this slope is 8.5 meters per second. Well, I can figure out how far it goes because if I do a velocity time graph where I'm traveling at 8.5 meters per second for 20 seconds, I take the area here. The area will be 8.5 times 20. 8.5 times 20. And 8.5 times 10 is 85, so 8.5 times 20 is probably 170 meters. So I get 170 meters there. That means this guy travels for a total of 170 meters, and this will be 170 meters. Now, I'm going to draw my dot here, and basically, since every dot is 4 seconds, I'll redraw that. Every dot's 4 seconds. I only need to represent this with 5 dots. They should be all about the same speed. Let me redraw this. All right, let me just change the boundaries here. So this will be over here. All right, so I have 5 arrows of equal lengths representing this 170 meters. Every dot's 4 seconds. So this is my motion map. Hopefully this makes sense. I can break this up. So 170 divided by 5, I would get 34 meters Does that sound right? 34 meters each time, so 34 meters, 68 meters, 102 meters, 136 meters, and then 170 meters over here. So that makes sense. All right, so in 4 seconds, I'm traveling 34 meters, essentially, is what I'm saying there. So there, this is all these graphs. I solve for unknown quantities, so I combine B and C. So that's what that is. I'm just trying to show you everything we've learned. We've just completely mapped out what this dune buggy is. All right, I have enough time. I'll go on to the next part of worksheet 5. All right, so this one, we are given a velocity time graph. And actually, we haven't had a lot of scenarios with this. So I think this is a good one to go over. This would be a great, hard test question to get, as you're only given the velocity time graph. Some things to note. This is 7.5 centimeters per second up here. And notice it's centimeters per second. So not meters per second, what we've been used to. So they want us to find the area, the displacement, from 2 to 3.5 seconds. That would be from here to here, roughly. Now, the way we could do it, before you could have counted the boxes, but this is a reason why you can't just count the boxes. Our increments go up by 5, and not only that, we're in between boxes. I couldn't even tell you if this is how many boxes that is just from looking at it. So I'll take the area of this. So I'm traveling at 7.5 centimeters per second, and the amount, my width of the box is from 2 to 3.5 seconds. That would be 1.5 seconds. So these cancel. So 7.5 times 1.5, that should be 11.25 centimeters. Now they want it from 5 to 6. So this one's not too hard. The only thing you need to remember is that it's negative 10 centimeters per second times 1 second. You'll get negative 10 centimeters. They want us to draw a graph. I'll let y'all draw this graph, but I'll tell you this now. You should, I'm going to draw on a different graph here, just because this is all kind of scuffed. So y'all can do what you feel like you need to do. Don't be too worried about making it really neat, but the neater is the better, the more accurate it will be. So I'll see you guys in a second. So actually, I'm gonna kind of show you how I'm gonna do it. So the first thing is we have to assume a starting position of 20 centimeters at t equals 0. If they did not tell me that, I probably would have started this graph at 0. Why that's important is this highlights the issue with velocity time graphs. Velocity time graphs, they're really nice. If I point at an object and I say, what is its movement at 3 seconds? I know exactly how fast it's moving, but it's kind of hard for me to tell where it is. This is telling me I'm starting at 20 centimeters. I would not be able to tell that if, unless they had told me it. So what's hard here is I can go up by 7.5 centimeters per second, but that's kind of hard to tell. So maybe it would be easier if I figured out what its displacement is for this entire section. And that would be 7.5 centimeters per second times 4, which would be equal to 30 meters. Now, note this, I do not end at 30 meters. All that is telling me is that I gain 30 meters. So by the 4th second, I'll be at 50 meters, and that should be at 50. Hopefully that's not too confusing. The next 3 seconds, I'm traveling negative 10 centimeters per second for 3 seconds. So I'm actually going to lose negative 30 meters in this section, centimeters. And so I'll go down 50 minus 30. I'll be back actually at 20 again where I started. But I do this at a faster rate, right? Only over 3 seconds. I stop for 3. And then I actually go up positive 10 meters in these last 2 seconds. So I'm going to end at 30. There we go. Note, this actually looks steeper than it really is because I scrunched the numbers up here. So this is why you should scale better than what I just did there. All right. Last thing we're going to do, motion map. So I've got this motion map. I'm going to go by increments of 10, 20, 30, 40, 50, 60. I'm going to say the units are centimeters down here. Great. All right, I start at 20. And basically, I'm going to get to about 50. I'll go 7.5. And then I will stop for, no, sorry, I'll go backwards -10. I'll stop for 3 seconds. And then I'll go forward by 5 centimeters per second. And I start here, I end there. If you can do that, I think you're going to get a very good grade on this test. If you still have some struggles, I would go back to actually other worksheets and see those problems first and before going to this one. So, all right. Thanks, guys, and I'll see you for acceleration.